Okay, so this is question 3, part B from the 2012 scholarship paper. It's not very related to the first part, which was all about vanadium and its various oxidation states, and then suddenly in part B we're talking about proteins and amino acids. And this can happen on your scholarship papers, and you need to be aware of that too. Um, so anyway, this question is about proteins. Proteins are polymers of amino acids that contain different side chains, indicated as are in the diagram below. The properties of proteins are largely determined by the sequence of the amino acids from which they are made. So the side chain or there can be any of these here, and there are other side chains you can have. There's about 20 essential amino acids in the body. And then the pKa is given here of any side chains where appropriate. So the question here is, the first part is, classify with reasons whether the amino acid side chains in the table are charged, polar, or non-polar at physiological pH of 7.4. The first thing I'll do is just talk about polarity because it's easy to eliminate those pretty quickly. Aniline will be non-polar. Aspartic acid and glutamic acid, we have to discuss the effect of pH on them, and lysine as well, because we're given pKa values. Serine has an OH group, so it's going to be polar, and that's because of the difference in electronegativity between oxygen and hydrogen. So you get a polar side group there, and overall the molecule is going to be polar. So to talk about the aspartic acid, glutamic, and lysine, we need to consider these pKa values and what's going on here. So I'm just going to take a different page now. And for the first situation, for the acids, we have that carboxylic acid terminal side group. So whether this is aspartic or glutamic, it's the same principle applies. And you have an equilibrium setup where this terminal proton can be lost to form the base species, the carboxylate ion, and that's the base species. So we call this the base species. This is the acidic species or acid species. And then the situation for lysine is that you have an NH3 plus group, and then there's an equilibrium established there as well, where you form NH2 plus your H plus, and this is the base species, and this is the acid species. So because we have an equilibrium, we can write an equilibrium expression or constant, and the equilibrium constant is going to be the Ka. Now the pKa is where we get our Ka from, so the pKa for aspartic acid or glutamic was given to us as being 4. And if you remember from level 2, or level 3 for that matter, 10 to the minus pKa will give you your Ka value, which in this case is 1 by 10 to the minus 4. And then the pKa for lysine was equal to 11, so 10 to the minus 11 gives you 1 by 10 to the minus 11. And a Ka is a measure of how good a weak acid is at dissociating in water. So the larger the Ka, the better at dissociating. Now, if we go back to the question, so in the question it says, what would happen the acids or the lysine at a pH of 7.4? So we need to discuss the relationship between pH and pKa. Now the relationship between pH and pKa was best described by two scientists called Henderson and Hasselbalch, and they came up with the Henderson-Hasselbalch equation, which is the pH is equal to the pKa plus the log to the base 10 of the concentration of the base species over the acid species. So we're considering this species and this species, or this species and this species. Okay, so that's the relationship between pH and pKa. So now the situation we're looking at is, if the pH is greater than the pKa, then in this case we have a pH of 7.4 is greater than the pKa of 4, then the base species will be favored. So for glutamic acid and aspartic acid, it's the carboxylate ion which will be in existence in water or an aqueous system at pH 7.4. So in the blood, that's the species that will predominate. Whereas the opposite situation arises if the pH is less than the pKa, as in the case for lysine, which had a pKa of 11, the acid species will be favored. And so that's the charged species, which was this one right here. The acid species will be favored. Now this is important when we look at the second part of the question. So at physiological pH, this one will be charged. This one will be charged negatively for the base species. This one will also be, glutamic acid will be negative for the base species, and then this one will be positive for the acid species. And then we have nonpolar, polar, and also leucine is nonpolar. So that's accounted for the charge, polar and nonpolar state of each of these side chains at a pH of 7.4. And the last part of the question, discuss how the nature of each side chain could affect the observed tendency of proteins to fold up in aqueous solution. So what I'm going to do here is I'm just going to piggyback on the answer from NZQA and make some notes to it. So let's get down to this part of the question. So you can see there part B, alanine was nonpolar. Aspartic acid will be in the negative or base species because the pH of 7.4 was greater than the pKa of 4. Glutamic acid is the same as for aspartic. Leucine is nonpolar. Lysine, the pH of 7.4 is less than the pKa of 11. So the protonated form, or the positive NH3 plus form prevails. And then serine is polar due to the difference in electronegativity between both oxygen and hydrogen. And then this final statement then, hydrogen bonding to water would be expected for polar groups and the amide backbone of the protein. Okay, so hydrogen bonding, this could be for the OH group of serine. So this could be serine that can hydrogen bond to water, so the hydrogen to the oxygen rather. And there's your water molecule, so that's hydrogen bonding. You could also have hydrogen bonding, that's the main one. For the other two, then, for the aspartic acid or the glutamic acid, which are going to form their base species, they're going to be negatively charged. So this is for glutamic or aspartic. That negative charge can be surrounded by water wedges. So if you remember your water wedge theory, this is what we're talking about here. And they will completely surround that negative charge, separating those amino acids. The positive charge of the lysine, that will be surrounded by water molecules, but in the other orientation where the oxygen is facing them. That's the point of the wedge. And then what else to talk about here? Non-polar groups will essentially be repelled from water as they cannot make new hydrogen bonds to water. They can, excuse me, however, have favorable instantaneous induced dipole interactions with each other. So this is in essence intermolecular bonding. Weak intermolecular bonding, also called van der Waals forces. And this could be, for example, in leucine, which is nonpolar. Leucine has 1, 2, 3, 4, a 4-carbon chain, 1, 2, 3, 4. And you could just have those carbon chains weakly intermolecular bonding. Thus, proteins should fold up to allow nonpolar groups to engage with each other and not be exposed to water, and to have polar or charged groups with stabilizing interactions with the solvent of water. So if this represents a folded protein, you'll have your charged side groups out facing the water. So there's your water, charged side groups. And then in the inside, you just have weak intermolecular bonding between your non-polar side groups. Non-polar, non-polar. And that's how proteins assume a three-dimensional structure. So that's the answer to part B from question 3 in the 2012 scholarship paper.